spatial-temporal scales. We know that a white box model needs many detailed input data. They are time-consuming and computationally expensive when we want to model a large area like urban. And on the other hand, the black box models lacks the physical interpretability and needs lots of samples and reliable input features to be trained. So it seems that this integrated methodology is the optimum point between these two approaches. We saw satisfying results in all spatial-temporal granularities. We got that many factors affect the performance of the model, including building size, magnitude of the energy use, and spatial events. And we got that the deep neural network adopted could successfully overcome the uncertainties and capture the nonlinear interactions among the buildings. Future work can be done on testing over a larger mixed functional area like an urban scale, assessing the performance on other energy carriers like gas and chilled water, and employing sequence-to-sequence deep learning algorithms like long short-term memory, since we are dealing with time series data, and adding more input features in both steps may improve the model performance. Thank you for your attention.
Thank you.
Thank you very much. I would like to ask if we have any question for Amin. No question? Okay, because it's Friday afternoon, so thank you very much. And see you later for the final ceremony. And okay, Omar, are you okay? Omar Perez?
You have to stop to share the screen, please.
I think I lost the
Yes, we need. Okay.
No, you can.
So Ramin should unshare his screen, and I would like to ask Omar to switch on the camera so that we can see you.
Ok, mi sta andando il terzo.
We cannot see you.
Forse, si va.
Just a moment, please.
Yeah.
Perfect.
Okay.
Can you see me now?
Yes, we can hear you and even see you. So, Professor Daniotti already introduced your work, so please start sharing your screen and your presentation. Okay?
Perfect. Thank you very much, and sorry for being
Ok, l'hai già fatta partire?
No.
Ah, ok. C'è tutto il mio corso di laurea, sì. Sì, altri 20 minuti.
Alright.
Più o meno siamo in orario, dai, secondo te. Ormai non sto facendo domande a nessuno, se le fanno a me per primo, ce la fai io di no. No, però non hanno fatto domande a nessuno. No, non le facciamo neanche a noi.
First of all, we should talk about the hospitality in Mexico, national country. Then we will study the thirdly, we will study the local.
Ah, si sente.
Then we will explain in a second way how does the building execution plan is created and the different documentation process that will be held. And finally, we will speak about the main advantages of using these structured maintenance plans against the traditional process held right now in Mexico. In order to understand the challenges that the constructions will happen and the maintenance process, it is important to understand how does the construction in Mexico is held. As can be seen in the images, mainly this construction is based on wet construction systems, which includes cast-in-place reinforced concrete structures and masonry walls, and in a less spread way, prefabricated materials. Then, all these constructive materials are highly affected by the climate influence. As we can see in the images, the hurricane season in Mexico is very important, as from May to October this will derive in a very wet and rainy season, and also we can find in the northern part of the country very arid climates, and in the southeast part of the country humid and tropical climates. These factors, in addition to a poor maintenance culture in Mexico, derive in a very quick decay process and have maintenance processes that are very costly, because currently the maintenance activities are done when the constructive materials are totally failing. How can we create a structure plan to support these maintenance activities? In order to solve this answer, it was decided to study the different standardization available in order to define an information management strategy and the different requirements to be followed. And it is decided to divide the standardization analysis in 3 different levels. Firstly, studying the ISO normativity related to the asset management, to the BIM execution plans supported by building information models, and the life cycle analysis and prediction. In the second level, it is studied the national normativity of a success case like this, the United Kingdom, where these building execution plans are a reality and a legal requirement. And thirdly, we will discuss the national normativity most recently released in 2017 in Mexico related to the building execution plans and its requirements. Now inside the normativity, here we can see that the information is treated and organized in a different way according with the phase that the building is in. In the left side, we can see the delivery phase, which includes the preparation, design, and building processes. And then in the right side, the operative phase, which includes all the operative life of the building. That is the one that we are interested in. And one of the most important things during these processes are the trigger events. These events are the ones where the information is generated. In the operative phase that we are interested in, the trigger events will be related to the maintenance process that this building will have during its entire life cycle. So, in every maintenance process, information will be generated and recorded in the Asset Information Model, or AIM. And here, in this graphic, in a very basic way, it is explained a hypothetical case where
staccate vuoi fare per sicurezza?
where it is treated a hypothetical case with one without maintenance. The case without maintenance is in the both line, and here we can see that the decay process is pretended to be quicker. And having an organized structured maintenance process, it can be easily reduce this time and have the building in optimal conditions for a longer time. Then, how can a building information model can improve this structured maintenance process? Here we have some benefits. First of all, it enhances the collaborative working between specialties. This means that all the interested parties and the specialties involved in the project can have the information at the time and in an organized way, so everyone can work independently and sharing information. Secondly, it allows efficient process information, as the building information model inside its structure allows the user to input all the information in some volumetric containers that we see in the model. So all the processes can be input in an easy way. Thirdly, it links all the information stages in an source. This is an important requirement for the asset information model, as according with the standardization available, to comply with this maintenance process, it is really needed that we we have a centralized source of information related to this model. And finally, coming back to the collaborative working, the versatility with other softwares. This means that the building information model can be shared with different softwares according with the different specialties and in the form of an IFC. Then we will pass directly to the study case. It is a medium-sized elementary school located in the central part of the country in a municipality called Santiago Tulantepec. This small school has an approximate surface of 750 square meters divided in 3 different levels. Thanks to the information provided by the building owner and the architect in charge, it was created this building information model, and in the first step, it was decided to understand how those the different sectors of the school are divided in the form of plans, as we can see in the images. And there were studied the different stratigraphies or constructive solutions that the school has. Here we can see these vertical closures or walls that are in total 5, and 3 different horizontal closures or roofs. And also inside the model, it is very easy to identify these different stratigraphies inside the plans. So it is very easy to understand and easy to quantify inside the Revit model, as we can see here in the plans. Then, in the very first part of the year 2020, it was done a preliminary inspection in order to know the current state of the construction. And we can say that after 25 years of operative life, the school has not suffered so much damage in this moment. But it was important to show some important failures that need immediate attention. In the first image, we can see the top roof that has been delaminated the external surface of the mortar that was pretended to work as a part of the weatherproof layer. This is an important failure and needs to be treated immediately. In the second part, we have one of the external facade walls that has suffered fluorescent spots. This is due to the evaporation during all these 25 years. And thirdly, we have the third image that is due to a bad execution on the service entrance sleeve. The infiltration happened and affected the concrete surface and external mortar layers. Well, once we know the local study case and the factors that will affect this, now it's important to know how does the building execution plan is created. And according with the standardization available, we have 4 different information requirements that needs to be complied in order to build this building execution plan. As we can see, these are organizational, asset, project, and exchange information requirements. This will derive in the different information models that we need. In the case is the AIM or the PIM. Then coming back to the national normativity, here we can see the main requirements according to the law, and can be seen that from point 1 to 6, it matches approximately the information requirements that we have seen in the previous graphics. So, in order to identify these requirements and compile them and in form of agreement, it was generated a unified format where all this information can be input and discussed, as we can see in this slide. First of all, we have a very brief introduction, we have the project information, and the different requirements for all the interested parties. Then, the key personnel required to follow this execution plan and the agreement signatures so everyone can follow and refer this document for future processes. Then, it was needed to follow a logical step where do we need these different processes and what information needs to be generated. So, they were generated these EEP diagrams where we have the different steps and additionally the information process or the documentation that needs to be referred and generated. And always following decision steps, as we can see in the right side, as we are evaluating the maintenance. In this case, it can be preventive maintenance that could be scheduled and organized, or reactive maintenance that happened unexpectedly and needs to be treated immediately. And then following the diagrams, we can see the different steps we follow, and always following the compilation with this document that we presented before, the beam uses and goals. If it complies, the activities could be followed, executed, and approved, then passed and archived inside the AIM. Otherwise, the process needs to be repeated and until the process is approved and complies with the information requirements explained before. Then we will explain in a very brief way the different documentation that was generated in a very simple case. As can be seen in the images, we are talking about the component F02, that is the top group that we have seen with the delamination, and it's explained the different constructive materials that they are composing it, and in a more specific way, all the performance factors that it has. This is thanks to the technical brochures and the information provided by the provider. Sorry. Then, once we identify all the elements, we can make an inspection format where all the failures can be recorded and explained in a simple way. And then, supported with this inspection process, we can speak about a failure profile with all the details about the profile and an evaluation of it. As can be seen in the image, the performance factor in here, it is decided to be as 4, unacceptable, as the delamination of this component can compromise in a very severe way the weather tightness of the roof. Then, once we evaluate it, it can be presented as suggested sequence of steps to fix this action. And here we are talking about the layer replacement. Once we agree with that, we can go to an operative activity plan, as can be seen in this image. Here we can see that it is explained all the resources in terms of workforce and tools, and the total cost that this activity will have. And finally, we can reflect all these activities in a form of a schedule, where we can have the planned and non-planned activities. As we have explained before, all the complete layer rehabilitation, in this case, is considered as a reactive maintenance activity that must be followed with operational maintenance and results report meetings. Then we will explain in a very brief way how can we input all these information parameters inside the Revit model.
Oddio, pazzo questo.
Okay, once we are inside the Revit model, it is important to understand how does Revit interpret the information that we are putting. As we have commented before, all the building components have 6 different constructive layers, and these constructive layers are interpreted in Revit as Revit parts, and every one of these Revit parts will have its own parameters, and this is totally individual for each one of them. As we can see, to complete all these parameters will be very time-lasting, and mistakes can happen in a very easy way. So it is important to have a very safe control and a very secure way. How can we input these parameters without mistakes? And for that, it is decided to rely on a tool inside the Revit model that is called Dynamo, which allows us to make very simple programming in order to identify these systems and apply the information parameters that we want. Once we are in Dynamo, here we have the searching criteria in the first steps. As commented before, we are looking for parts, and in the bottom part, we are seeing the searching criteria that we are looking for. In this case, we are looking for the building component layer, and specifically the W01.1. Then, once we apply this searching criteria inside Dynamo, we can see that we find 200 more than 200 elements. But once we find this searching criteria with the W01.1, we have only 44. So all these components are very easy to identify, and then thanks to this very simple script, can be added all the parameters that we need. Now, once we are inputting all the parameters and we verify that the information is correct, it is very easy to input all these parameters in just one step. That is to run the script and wait that this is done. Once back in the model, we can randomly check the different components, and finally we see that all the information input that we have done in Dynamo is done correctly. So all the information matches and is done in a very quick way, comparing with the traditional process that is input by hand. Finally, we are talking about the conclusion. Finally, we can say that thanks to these building execution plans, there is a positive collaboration between parties, and this is a crucial step in the current building industry, because even now we need more collaboration between all the interested parties and all the specialties. So if we comply with this, the process could be much easier and much quicker. Then, as can be considered as a drawback, that it is needed an initial higher demand of time and organization, as it is required to deal with all the specialties in order to create a correct building execution plan. And also, we are talking about a technological transition, because in Mexico, right now, the BIM technology is available, but it's not so spread. We still rely on a 2D drawing process. But if we apply these BIM execution plans and we believe in the BIM execution process, we can have benefits in future, as happened in countries like the United States or in the European Union. And once we believe in these building execution plans and the BIM technology, we will improve and enhance the national building industry that is very needed in Mexico, as we have very good construction, but the standardization is still poor. So with a little bit of effort, this can become a reality. And then this is everything for the presentation. Thank you very much for your attention.
Do we have any questions from our board? Okay, so we can say that on a late July Friday afternoon, no question have. Thank you very much, Omar. And so there are no questions for you. So feel free to leave the stage to the next team of students, who are Joseph Battistesso and Luca Galli. Okay, please switch on your camera. Luca, okay. Marco, okay.
Good morning.
Good morning.
Okay, so who is sharing the screen?
Yeah, I'll take care of it.
Luca, okay. So before you start, I would like to ask Professor Gastaldi to shortly introduce your work. And we have already connected to this session even Professor Prannoy, right?
Yes.
Suraneni from Miami.
I want to thank Professor Prannoy to be here. For us, it's a big honor. And the reason why Professor Prannoy is here is because Luca and Marco spent a period in University of Miami at the lab of Professor Nani and Professor Prannoy, in order to make the test that is presented in this case. I think that Luca and Marco can present the cases better than me. So let's start.
Thank you. So you can start.
Okay. So, good morning and good afternoon. I am Marco Battistessa.
And I am Luca Galli.
So, and today we will be presenting our master thesis work carried out at the University of Miami and planned at the Politecnico di Milano. Our thesis is about a new experimental test to evaluate the bond durability of the GFRP rebars in concrete elements, and also about a non-destructive method to detect this kind of reinforcement. So let's introduce our work. So Luca, please. Yeah, here we go. So as we know, the steel reinforcements are subjected to electrochemical corrosion during the service life of a concrete structure, especially if these are exposed to aggressive environments like the marine environments. So the resulting deterioration leads to high implied costs related to maintenance and safety over the long term. To overcome this problem, alternative rebars were introduced in the last decade, made out of non-corrosive materials such as fiber-reinforced polymers and especially the glass fiber-reinforced polymers, due to their competitive cost and also good mechanical properties. However, also the GFRP rebars might show other issues related to their durability in concrete, because external agents like moisture content, alkalinity, and also high temperature may degrade the bond of this kind of rebars. So for these reasons, in-depth studies are becoming necessary to better evaluate these effects. So nowadays, different laboratory tests are used to assess the bond strength between the GFRPs and the concrete. So usually specimens under accelerated exposure condition are tested to evaluate and simulate the bond and the loss of performance over the long term. So among these test methods, the direct pull-out test is widely used because it's simple and also requires small specimen. Other tests like the beam test and also the beam test better simulate the real stress state condition of a reinforced concrete structure. However, these tests do not apply on specimens taken from existing structure. So on the other hand, as on field test, the scanning electron microscopy is the only way to observe the aging effect of GFRP rebars on specimens that comes from a real structure. But of course, this test is not possible to measure the bond strength in this way. So regarding the on-field test, there is a need of a way to measure the bond strength, and also there is no literature on how to detect this kind of reinforcement inside the concrete. For this reason, just explain, this master thesis works aim to define a possible test able to evaluate changes of the adhesion between the GFRPs and the concrete, and define that this may also be performed on specimens taken from existing structure. Secondly, we want to provide guidelines for the definition of a non-destructive test for the detection of this kind of reinforcement. So during our experimental program, we chose the materials according to a previous thesis work where the new test has been introduced, so in order to make comparison with them. All the specimens were made out of the same kind of concrete, whose boundary is composed by Portland cement and slag, and also the same kind of reinforcement commercially available, which is covered by a sand coating and a helical wrap of the surface. So in this way, we want also to limit as much as possible the variable to be studied. So then, first we performed several compressive strength tests in order to have a mechanical characterization of the concrete. So we carried out tests after 7, 14, and 28 days of curing in a moisture room at 23 degrees and a relative humidity of 95%. So let's talk about the punch test, which is the methodology proposed in the previous thesis work to evaluate the effect of different environments on the adhesion between the GFRP and the concrete. So this test originally is already available in the American standard, but is used to test the structural chemical anchor. So starting on this basis, it has been modified, trying to define a proper setup for the new purpose. The specimens, as you can see in the picture, are cylindrical slices, 3 cm thick and 15 cm of diameter. So compared to the tests previously seen, the punch test provides several advantages because, as you can see in the figure, the specimens are much smaller than the one of the pull-out test. And in addition, thanks to its test methodology, it's the only method that can be applied to specimens taken from existing structure. However, specimens of such geometries might be affected by the splinting of the concrete while the load is being applied. But to avoid that, we studied the effect of the confinement forces applying a T-bolt steel clamp along the circumferences of the slices in a range from 0 to 14 Nm, and also the specimen support configurations, where differences were about the interlayer between the specimen and the concrete. In the first configuration that we tried, we used an interlayer of WD-40 oil to reduce the friction coefficient between the concrete and the steel plate. Then we tried to use a neoprene mat, 1.5 mm thick, and also a third configuration. In the third configuration, we tried to apply a sulfur mortar capping on the bottom surface of the concrete. Of course, in these last two configurations, there is an hole in the middle of the interlayer to allow the rebar displacement.
Well, now let's have a look at what we got in terms of results. So here we can observe the results obtained by the compressive strength test performed at 7, 14 and 28 days of curing. And also we can see the estimated evolution fitted according to Eurocode 2. While on this graph we can see the mean compressive strength of each curing period highlighted and compared to the one obtained in the previous thesis work. You can see that after our first quicker development of mechanical properties in the concrete we used, we got very similar results at 14 and in particular 28 days of curing with values around 40 megapascal. From this point of view, it appears evident how the two concrete are comparable. This bond stress versus slip diagram points out the three typical results that we have observed during all the punch tests performed. In fact, no matter the kind of support configuration we use, similar trends have been obtained depending on the occurrence or not of the splitting phenomenon in the concrete slices. The orange curve is an example of trend that we have obtained in all the slices recorded as fully splitted. As you can see from the picture, those specimens were characterized by a fully developed crack. The blue line instead shows us the specimens recorded as partially splitted, where a slight crack on the bottom surface of the slices were recorded. The green line will explain the typical trend in which no evidence of concrete splitting were recorded. In the first two cases, we can see that an initial discontinuity arises in bond stress values around of 4 or 5 megapascal. In this range, the average tensile strength of the concrete that was estimated equal to 3.5 megapascal might be reached. So the presence of this discontinuity seems to be related to the concrete cracking. In the samples partially splitted, we can observe that after the discontinuity, there is a further increment in the bond stress. That's why in such cases, the crack propagates until it meets up the opposition of the confinement action provided by the steel clamp. In fact, increasing the tightening torque applied, the discontinuity becomes shorter and the maximum bond strength becomes higher. At the end of the punch test, a visual analysis of the GFRP rebar surface has been carried out to evaluate the failure mode. Well, we classified the failure mode as failure at the cementitious matrix, failure at the rebar surface, failure on the interface between concrete and reinforcement. In all the rebars observed, we have seen the three types of failure in different percentages. Okay, let's see this graph. So we have the data of the not split specimen of the three different configuration system, and also we have the global averages that of the rebar analyzed and grouped as splitted, not partially splitted, and not splitted. This graph shows similar results among the three configurations in case of not splitted samples, where we can see that a higher percentage of failure occurred at the river surface. In case of partially and fully splitted, this percentage decreases, while the one on the interface increases up to 30%. Looking at this graph, we can see the maximum bond strength values obtained in all the punch tests performed and according to the different support configuration. The capping was the support configuration in which the highest number of values were recorded as not splitted. It was experimentally determined that a tightening torque at least equal to 4 Nm should be applied to the steel clamp to guarantee this condition. A tightening torque of 10 Nm is necessary in case of WD-40, while a 40 Nm has been found necessary in the neoprene configuration. A drop of values were recorded in the splitting displacement, and when no splitting occurred, and no matter the configuration we used, we have identified similar bond stresses. And this trend was also confirmed by the results of the visual analysis. The difference in the tightening torque applied, therefore, may be related to the displacement support configuration. In fact, in case of capping, an additional confinement action is provided by the support system itself, thus explaining the lower tightening torque needed. While on this graph, we can see the data achieved with the neoprene configuration and again compared with the one of the previous thesis work. Here, the two configurations are very similar. In fact, both of them had a neoprene layer, and that allowed to reduce as much as possible the variables of the test. We can see that for lower tightening torque, in both cases, the two configurations, these configurations are not suitable to avoid the concrete splitting, while for higher tightening torque, the results seem similar to each other. In fact, it should be noticed that the specimen of the previous work, and here reported as not splitted, however, have shown the same discontinuity in their graph that we have previously analyzed. These results confirm the indication of the procedure to be used to perform the punch test. The data that we have obtained from the concrete slices are fundamental to better evaluate also our setup for the sample extracted from real structure. From that purpose, the punch test was to be used also on cores extracted from reinforcing concrete beams that we have cast, and we can see here in the picture, and subsequently on cores extracted from real structure. Our setup was already studied, and GFRP reinforced concrete bridge was already identified. It was planned to extract several cores from different parts of the structure to evaluate the effects of the marine environment on the adhesion between GFRP and concrete. However, while we were developing this part, the unpredictable spread of the COVID-19 stopped all the research activities at the University of Miami, so it was not possible to complete this part of the tests.
Okay, so in the second part of our experimental program, our reinforced concrete slab has been produced to run the non-destructive tests on it, and several diameters have been embedded inside in order to test the instrument sensitivity. Among the available non-destructive tests, the ground-penetrating radar and the ultrasonic tests have been selected because they seem the most promising, since they have no material dependence. So with those two instruments have been performed different scan. The first scan, here let's have a look at the result that we got from the one-way line scan performed with the ground-penetrating radar. Here we can see the radar ground view compared to the migrated heat map view. So the radar ground view is, for those who are not comfortable with the GPR, is the typical visualization mode of all the GPR instruments. And their objects are recognizable through their parabola that you can see there in the picture, where they are the tags, but the tags have been manually placed. So as you can see, the migrated map view, on the other hand, is generated in post-processing. So as you can see here, the migrated map view is more easy to be interpreted. So for that reason, we prefer to use this kind of image. So here we can see better the results from the one-way line scan, and as you can see, the rebars in the upper layer have been more clearly detected, except for if we are overlapping the picture of the slab, this is clear, and except for the smallest one, which is the rebar number 3, whose nominal diameter is 10 millimeters, which is not being detected, as well as the rebars in the bottom layer, except for the rebars number 5, which is nominal diameter is 16 millimeters. So then we performed a cross-polarization scan. Here again, if we overlap the picture of the slab on it, we can see that generally all the rebars have been clearly detected, so it's been possible to obtain higher resolution results. But also having higher resolution result means that also more anomalies in the medium might be detected. So just should keep in mind that when balancing the setting, just be careful about the noise. So then we performed an area scan, which should be performed using this special paper given by the GPR manufacturer. The area scan can be analyzed in augmented reality view and also in a 3D view. As you can see, this visualization gives a broad understanding of the spatial distribution of all the targets inside the concrete. But considering our purpose, we believe that more useful information can be acquired from the previous two scans, because you can acquire like the target position and also depth and distances. So then, at the end of our experimental program, we performed a line scan with the ultrasonic test. And again, if overlapping the picture of the slab on it, generally we cannot really say where the rebars are. The tags that you can see there have been manually placed, but there is not a clear detection of all the reinforcement, and also there is a great noise from the backwards. So the preliminary test performed shows that the ultrasonic test seems to be not effective to locate this kind of reinforcement. Nevertheless, further tests with different type of concrete and also an on-field application are essential to evaluate the real effectiveness of the ultrasonic test.
Okay, from the test carried out on this thesis work, we can draw the following conclusion. So we have combined different combination of confinement forces and also different specimen support configuration to define a proper setup for the punch test and to avoid the concrete splitting of the sample. So a loss of adhesion has been measured in the partially and fully split specimens, and also we have observed that the occurrence of the concrete cracking depends on the flatness of the specimen and also on the confinement force. For the capping, that is also the configuration that allows to obtain perfectly planar surfaces of the slices, a lower tightening torque have been found necessary to guarantee to avoid the concrete splitting, while higher values are needed in case of WD-40 and neoprene configurations. Also, the capping is a procedure that is largely used in the compressive stand test, so it might be used for the same purpose also in the punch test, since it does not require the time-consuming practice of the specimen preparation. In the visual analysis, has been observed that a failure at the rebar surface is higher when also the bond stress is higher. But anyway, as the most predominant failure mode has been always observed at the cementitious matrix level. The results compared of the one of the previous thesis work have confirmed the reliability of the methodology proposed and for the punch test. The ground penetrating radar proved to be an effective solution to detect even the small GFRP diameters, and also, as we have seen in case of overlapped bars. The ultrasonic device instead seemed not to be able to detect this type of reinforcement, also referring with the larger diameters. Anyway, further studies with different types of concrete reinforcement and tests on specimens from existing structure are needed to implement this type of test. Thank you so much for your attention.
Thank you too. Perfect time. Thank you. I'm trying again, but let's see if the trend is confirmed. Do we have any question for these two students, or these two candidates? No question. So I would confirm the trend for this afternoon. Thank you very much, and see you later for the final ceremony.
Okay.
Sure.
And we can invite now Saskia Sabatini.
Yes, hello.
Okay.
Hi, Saskia. Introduce your work.
Okay, so in the meantime, if you would like to start sharing the presentation. So, the University address the issue of cost optimality in the choice of optimal solution in terms of investment and energy saving for the renovation of a case study building located in Helsinki. So the study involved the use of IDAI's software and its multi-objective optimization tool for selecting suitable energy performance improvement measures. And in addition, the candidate worked closely with the software development team, and part of our work consisted of undertaking the software debugging activities. So good luck for your presentation and have a nice start.
Thank you for the introduction, Professor. So this thesis concerns this multi-objective optimization for the measures for case study located in Helsinki. So the main objectives here are to define the efficiency measures to maximize both the cost effectiveness and the energy performance of the building retrofitting, of course in compliance with the national requirements. Then the evaluation of the solution in terms of economic viability and primary energy consumption. And finally, the evaluation of the selected final solution in terms of national nearly zero energy requirements. So I wanted first to introduce you briefly with some selected data to the context. So this chart is the energy consumption share in residential building updated to November 2018. It is taking confidential statistics of data. So as you can see, the highest energy consumption is represented by the space heating. It counts for 68%, and thanks to the million square meter of residential buildings throughout the country, it is possible to calculate for the same year 2018 the average primary energy consumption, which counts for 224.3 kilowatt-hour per square meter per year. Looking at some more economical data, in this chart you can see the investment share, which is divided between building retrofit and new building projects. As you can see from the dark blue bar, the building retrofit share is every year more than 40%, and these data are taken from 2012. On the right graph, you can see some highlights I selected mainly for building retrofitting. Here you can see the annual investment growth rate. It is the gray bar. You can see every year it increased, except for 2 years, which were 2018 and 2015, in which a big drop occurred even in the annual share increase. This according to the statistics occurred by a national block of granted building permits. So looking at the study is located in the north area of Helsinki. It is an existing building. It was built in 1994. It belongs to the continental cool climates according to the classification climate of Copenhagen. as we see from the plans, the layout is almost symmetrical on both axes, and also the plans are very regular for all the four floors. We have a total area of 1,400 square meter and a surface to volume ratio of 0.25. From this perspective views, you can see the most typical feature of the building, which are these semi-closed balconies, which in the energy model they act as external fixed shading. Looking some of the input data, so as Professor introduced, the software use was idealized. This input data regarding the construction, we have an envelope average regarding the clear glass glazing of 1.8 watt per square meter per Kelvin. This was transmitted as a 0.242. On the far right, you can see thermal bridges values. I reported these values because this data were taken from the ISO standards because there weren't any specific data for the case study. So it should be considered when later we'll introduce the baseline that this number could be a bit worsened because these values from the other standard tends to overestimate the effects of the thermal bridges. Regarding the internal gains, we have a standard average gains for all of them except for the occupancy, which count for 28 square meter per person, which is actually a standard occupancy rate for this type of building category in Finland, which is a block of flats. Looking at the baselines, so the baseline is the current state of the building. It counts for a total primary energy consumption of 248.9 kilowatt hours per square meter per year. Looking at this data in terms of primary energy share, it is possible to see it counts for 83%. This 83% is for heating, and looking at this data in terms of the energy share, it counts for 85% with zone heating, against only 15% with domestic hot water. The energy requirements that constitute the target of this work were two. The first one is building retrofitting requirements. These are regulated by the National Building Code of Finland. It is a percentage according to the building category that should be reduced from the U value calculator of the building. For this case, which are a block of flats, the percentage was 50%, meaning that the minimum target primary energy consumption accounts for 211.5 kilowatt hour per square meter per year. On the other hand, we have the nearly zero energy building energy requirements. These are set for new apartment buildings. At this moment, this is also let's say a setting that is used even nationally for the existing buildings. So it counts for 116 kilowatt hour per square meter per year. So the optimization is composed by two objective functions. These are conflicting between each other. The optimization is the minimization of both the global cost. This is calculated in euro per square meter, and the primary energy consumption. So the global cost is calculated via the net present value, which is a financial method on a calculation period of 30 years, while the primary energy consumption is directly the outcome from the IDA's dynamic energy simulation software. Note that by choice, both the functions were equally weighted. This means that the approach at the end for the final solution was a posteriori, so the solution lies on the field, which is
analitici, quindi tipo non so, dei
regarding the
tabelle,
measures selected, so there were
queste sono
grouped
dei
into two main
collegati.
packages. The envelope system, you
Abbiamo
can
visto
see
tutte
there
le
are two
varie
variants of
le
them.
percentuali
These
del
include the
mondo
insolation thickness,
visivamente.
the glazing thermal transmittance,
Questi
and the
sono
envelope
super
tightness.
Invece
While on the
da,
other
non
hand,
ce lo
we
seguire
have
da qua.
the technical
Dal
system, again two variants, and this
Questi
package
sono dei
include
PPR,
the
usiamo Giovanni.
more plans and implementation of other system. We have an example solar-based electricity and thermal system dimensioning, also estimation of pre-existing ventilation in the building, and also implementation of different heating system. In this case was an exhaust air heat pump. Looking at a broader perspective, the optimization process. So the first step regards the optimization settings. So after some sensitivity analysis in the variance of the packages, the final number of optimization selected was 2. You can distinguish them by representation by the color. This is optimization number 1 and number 2, and these differ from the type of heating system concept. The first is district heating, which is the original and preserved system of the building. The second one is the implementation of the heat pump. Also in this step, these other settings were defined as the type of algorithm and also the dimension of the range variation for the parameters. The second step is for processing. This is the most time consuming. It is the iteration of the packages selected. In this case, each optimization took around 3 days. The final step is step 3. It is the finally all the output from the analyzer plotted. We have then 2 Pareto fronts, and through the process of decision making, the optimal solution is selected. Looking at the results from this graph, you can see clearly that the best optimization for both the targets is the optimization number 1. It has a lower primary energy consumption. It varies from 75 to 85 kilowatt-hour per square meter per year. This means a potential reduction from the baseline of about 70%, against the 52% reduction of the other optimization. Everything with even lower global cost. However, an optimal solution was chosen for both the optimization. So again, in the first optimization, we have the best objectives because we have best energy performances with a lower cost on a calculation period of 30 years, but it has also a higher investment cost. It is 94 euro per square meter against 82.8. So the investment cost is in this kind of project, the investment cost should be always calculated in a wider perspective, so in 30 years, but the investment cost is still important because in a real project this is the value that determines the financial loan. Further reasoning were about the Pareto points as a whole, so I wanted to evaluate which one of the two optimization was the more effective in terms of primary energy decrease and net present value increase. This means with the which one of the optimization achieves the best energy performances with the lowest global cost. Again, the results show that this optimization is the more effective, and this is why the final solution selected belongs to this optimization. So the district heating concept, it counts, so you can see in red for the final primary energy consumption, it is 78.2 kilowatt-hour per square meter per year. As you can see, it largely achieved both the targets that were the building retrofitting and the new energy building, with a global cost of 537 euro per square meter. I wanted to conclude this presentation with some highlights of this work. So it was a contribution for defining the applicable measures for this building retrofitting in this very typical Finnish residential block, especially for a country which is Finland, where this cost-optimized method is still not implemented yet in the codes. And also the contribution was in testing this coupling between scoped optimizer with for the first time with iGuys. Scoped optimizer was released in February 2020. On the other hand, this allows also to find some limitation. Of course, with multi-objective optimization, the time is inevitably a limitation for the accuracy of the results, and also there were some problems in some functions in iGuys. For example, there were some functions that didn't change dynamically in the optimization. So, in other words, there were some margin of energy improvement that were totally missed. To give an example, the thermal reducing data introduced before, these were steady for the whole optimization. So there was for sure some energy improvement that were missed in the results. Finally, to conclude some future developments, it would be interesting to include another multi-objective, another objective function regarding the CO2 emission reduction potential in order to evaluate the whole process, in the whole case, also with an environmental impact analysis. Thank you for your attention.
Thank you, Saskia. And yes, this is the second thesis of today that we see work within international cooperation. So really interesting work again. Thank you very much. I guess that we have no questions from the work. Indeed, yeah.
Comunque non stanno facendo domande.
No, so we can. No questions. Thank you very much. See you later for the final session.
Essendo cose talmente cioè un professore magari
I don't know if we have Professor Rececconi. I think that is not here. We have Alex. We have a team of two candidates, Alex Work and Sofia Fentani. And the supervisor is Professor Fulvio Rececconi. He has another, I cannot see him. Maybe yes, maybe. I don't know if are you in contact with him?
We were talking that we were supposed to be here today.
Yeah, he has at the same time an institutional meeting. Just in case he's able to join us, I'll give him the floor to say some word about your work. But now, let's see our time is going to start. There is a screen, okay, you can start.
Good afternoon. So before starting, we would like to thank Mr. Rececconi that cannot be here today for his help and guidance, and I let the floor to Sophia.
Good afternoon, and together with Alex we're going to present the thesis work of this semester about the construction of
Can you present to the